So let's see the definition of differential equations. A differential equation is a relation, and it's a relation between dependent variable, let us call it y, and independent variable, we'll call it x, and one or more differential coefficients of y with respect to x. Okay, so this is formal definition. Differential equation is a relation between a dependent variable, an independent variable, and one or more differential coefficients of y, which is dependent variable, with respect to an independent variable. Now in simple language, the differential equation is an equation containing derivatives. So for an example, let's take x dy by dx plus y sin x equals to 0. This is differential equation. It contains derivative of y with respect to x plus some other things. Then xy d2y by dx square plus, let's take e raised to 3x equals to 0. Then let's take another example. So d2y by dx square cube plus 3 dy by dx plus something, or suppose this is equal to 0. So these are some examples of differential equations. Now let us see what does it mean by order and degree of differential equations. So order of differential equation, it is order of highest derivative in equation. So now as you can see, this first equation here, it is first order because we have first derivative of y with respect to x. The second is second order because we have second derivative of y with respect to x, and this third equation is also second order because we have 2 times derivative of y with respect to x. So I can write this is first order, this one is second order, and this equation is also second order. Now let's see what does it mean by degree. So degree is just the power of the highest derivative in an equation. So as you can see here, the power of highest derivative, there is only one derivative and power of that is 1. So degree of this equation is first degree. So this is first order, first degree differential equation. This one is second order and power of the highest derivative is 1. The second order first degree differential equation, and here the power of highest derivative is 3. So this is second order third degree differential equation. So this is what it means by order and degree of a differential equation. Now, apart from exams, is there any reason to study differential equations? Well, there are many, but most important reason is we cannot understand physics or engineering itself without studying differential equations. They appear so many times in these streams. So let me show you some examples. Suppose we have this rigid support. This is a spring. It is connected to this block. And now suppose we displace this block by some amount, some distance. So block goes from here to here. X is the displacement. So in this case, the spring is elongated and there is restoring force developed in the spring. It is given by Hooke's law. And Hooke's law is the restoring force is equal to minus of K into X. K is the constant, we call it spring constant, and we can write force by using Newton's law as mass into acceleration. So it is m into acceleration is d2x over dt square. So now, as you can see, this is second order differential equation. Let's take another example. So we'll take an example of RLC circuit. This is resistor, this is inductor, capacitor, and we apply some voltage V. Now, using Kirchhoff's law, we can say that voltage we apply should be equal to sum of voltage drops or potential drops across R, L and C. So applied voltage equals to VL plus VR plus VC. This is voltage in inductor, VR is voltage in resistor, and VC is the voltage in capacitor. Now we know VL equals to L di by dt, VR by Ohm's law is I times R, and VC is Q divided by C. And we also know that current is equal to dq by dt. So using that, I can write V equals to L. Now we have derivative of I with respect to t, and I is derivative of q with respect to t. So substituting that, we'll get second derivative of q with respect to t plus R times I, which is R times dq by dt plus q over c. Now this is another second order differential equation. So we have second order derivative of q with respect to time. Let's take another example. So let's take example of wave equation. Now any wave has to satisfy this equation, d2y over dx square is equal to 1 over v square d2y by dt square. Now there are so many examples that I cannot enlist them all, but the differential equations come very often in physics. Okay, so now let's have a look on these equations. So here we have second order derivative of x with respect to time. Here we have derivative second order derivative of q with respect to time. So in these equations we have only one independent variable, and which is time. So these equations, they are called as ordinary differential equations. And you can see this equation here, we have two independent variables. So we are taking derivative of y with respect to x, and we are taking derivative of y with respect to t also. So this type of equation is called as partial differential equation, because here y is function of x as well as t. And correct way to write this is using this symbol. So this is partial derivative. So second order partial derivative of y with respect to x equals to 1 over v square into second order partial derivative of y with respect to t. So this equation is partial differential equation. Now in next few lectures we will concentrate on ordinary differential equations, where we will have only one independent variable. And after we are done with the ordinary differential equations, we will move on to the partial differential equations, where we can have two or more variables, that is two or more independent variables. Finally, let us study formation of differential equations. So formation of differential equations. So let's take an example. So suppose we have this circle, it is centered at origin, and we know equation of such circles is given by x square plus y square equals to r square, where r is the radius. So this is radius of the circle. Let's call it equation 1. Now we will treat this y as dependent variable and x as independent variable. So let's differentiate this with respect to x. So differentiating with respect to x, I can write derivative of x square is 2x plus derivative of y square using chain rule is 2y dy by dx, and r is constant, so derivative of r square is 0. Now let us divide this by 2, so I can write x plus y dy by dx equals to 0, or y dy by dx equals to minus x if I take that x on other side, and let's take y on other side, so it will be minus x divided by y. Okay, so we got this first order differential equation from this relation between x and y. Okay, so this is first order differential equation. Now any relation between y and x which satisfies this equation is called as the solution of this differential equation. So we can get that solution from here. We can rewrite this as y square equals to r square minus x square, and therefore y will be equal to square root of r square minus x square, both plus and minus. So this is the solution of this differential equation. And let's call this 2. So this is solution of differential equation, which is equation 2. Okay, now notice that this is first order differential equation and this solution contains this constant, one arbitrary constant. So this type of solution is called as general solution. And if we know the value of that arbitrary constant, so for particular value this will be called as particular solution. Okay, so for first order differential equation, its general solution will have one arbitrary constant. Now let's take another example. Now let us see final example for the lecture. So suppose now y equals to a sine omega x plus b into cos of omega x. Now let's take derivative of this with respect to x. So I can write dy by dx equals to derivative of sine omega x will be cos of omega x, but notice this omega x here, we don't have x, we have omega x. So using chain rule, we'll have derivative as cosine omega x multiplied by omega. So it is omega into a into cosine of omega x plus derivative of cos is minus sine, but we will have omega from here. So omega into b into minus sine of omega x. Okay, now let's differentiate this once again. So I can write this as d2y by dx square equals to, now derivative of cosine of omega x is minus sine omega x, and for this omega we'll have 1 omega in multiple. So we have 1 omega from there, so it is minus of omega square a into sine of omega x. And let's take this minus sign outside, so we get minus omega into b, and we'll get another omega from here, so it will be minus omega square b into cosine of omega x. Okay, now I can take minus omega square common from these two, so this is equal to minus omega square into a into sine of omega x plus b into cosine of omega x. So this is d2y by dx square. Now notice that this equation is y equals to a sine omega x plus b cosine omega x, and we have the same term here on right hand side. So in place of this I can substitute y, so I get d2y by dx square equals to minus omega square multiplied by y. Okay, so this is equation number 1, this is equation number 2. So we got this second order differential equation by taking derivatives of this equation, equation number 1. So this is second order differential equation. Now this y satisfies this equation, so this relation between y and x is general solution for differential equation 2. Okay, now notice that in this general solution we have these two constants a and b. So before this example we had first order differential equation and its general solution contained one arbitrary constant. Here we have second order differential equation. So for second order differential equation, we have solution which contains two arbitrary constants. Okay, so for nth order differential equation, its solution will contain n arbitrary constant, the general solution, and value of these constants can be determined by some initial condition given in the problem. Okay, so now we have seen few things about differential equations in this lecture. In next lecture we will start solving first order differential equations by various methods. Thanks for watching the lecture.